In this video, I'm going to be refactoring my CAN subsystem so that I can get it running on this board, which you can see on the picture here. For the most part, my CAN subsystem has been working, and I've been happy about it, but there's several improvements that I want to make to the code to make it work with, for example, my new device tree support, which I've been implementing in all of my drivers now because I like it so much. I want to clean things up a little bit, make it more modular. Also, for CAN open, I'm gonna need my implementation of the variable directory, and that's also gonna be moved to a driver instead of being just a library object. Because vardir will need to be shared between several other drivers, so it has to be. It kind of belongs in the driver tree. But starting with CAN, the first thing I want to do is, let's see here. So I have moved this to the device tree, and the last few things that I've been adding is just sort of registering the CAN device as into the array of all CAN devices, so that it can easily be found by other drivers. And one of the things to do there is that I want to use the same interface to search for CAN devices. I've implemented the interface as a set of simple templates, which allow each subsystem to be basically implemented like this. So I declare device class, and this automatically adds functions for looking up I2C devices in this case, and then there can be a few helper functions that help interact with the I2C devices. But then all I2C devices basically implement two functions, read and write. For the I2C case, write is basically just like a single transaction, and read is a combination of a write followed by a read. The specific implementations of the drivers implement this sequence of commands in order to be able to implement a read and a write. But for CAN, I've had the CAN subsystem is still kind of like the custom implementation where I don't use the templated code. So I'm going to add this. I'm going to make sure that this uses the templated code. One of the things with the CAN subsystem is that I had a list of listeners that I've added to the base class of all CAN devices. But I think I'm going to move this to something like a separate object, which would be I could call it, for example, CAN dispatcher or something. And the responsibility of this object is going to be to dispatch incoming messages to different higher level protocol drivers. Because in the case of CAN, you want to allow other devices, like other device drivers. You want to allow several device drivers to be attached to the same CAN interface. Because, for example, you can have device drivers that take care of certain devices on the CAN bus, and they would. The way this would work is that they would subscribe to certain messages from the CAN driver. And the CAN driver will then forward those messages to the specific listeners that are then able to handle those messages. And one such listener is the CAN open interface, which is implemented on top of the CAN device. So I'm going to move this. I'm going to declare my macro here. Declare device class CAN. And then I can remove this. Let's see, what is CAN port? So CAN port is actually kind of like the CAN device. This should actually be CAN device, not CAN ops. So I've improved my implementation of the generic interfaces. Originally, I just had the CAN ops as the pointer to like a handle to the device, but then I wanted to group them together and add a little bit more data to to the base class, so I changed this to be in a device class. So CAN device. Let's see, CAN message. We need that. Now counters can be defined here. CAN status. Yeah, I could probably clean a lot of this up. CAN state, like CAN counters can be just used by itself. And I had some idea with these structures. I'll leave them in place for now so I can see where they're used. I could comment them out. CAN message and CAN ops. And this will be CAN device. And then a few macros that simplify the usage of the CAN device handle. And then this will be removed. And then CAN device, and this will be all declared by the macro. I'll leave the code there for now so I can reference, for example, dispatch message and handler and a few details here that I may need to re-add somewhere else. And then in the CAN implementation, this would be the device class implementation. This would be define device class CAN, and this gets removed. And this is kind of the default handler, which will need to be moved to like a CAN dispatcher class or something. Can think about it later. Dispatch message. This is also CAN dispatcher. This doesn't really belong in the base class. And then register device. This is all implemented by the macros. Yeah, and this is just artifacts from the old implementation that did not use the device tree. And then the STM32 CAN implementation then implements this generic interface of a CAN device. And this will be moved like this. FTT. And I have to do it like this here, for example, checking if the device tree specifies CAN1 or CAN2, because right now I don't have any dynamic interrupt handling, and I don't think I need any, at least not right now. So I have functions that directly get included into the interrupt vector table, and they need to know which interface. They need to have a way of retrieving the pointer to the actual instance of the device, of the CAN device that handles a certain interface, and they do it using this global list of pointers here. And that's just to get a mapping between CAN1, CAN2, and the corresponding objects. Let's see what we get now. Right. This needs to include the driver. Let's see. Actually, I should be using ops for that because yeah, most definitely. So instead of pointing to the CAN device, it's gonna point to the member of the CAN device, which will point to ops. Let's see. Okay. CAN control param. So as part of CAN device ops, I need to have an ability to send the packet, ability to register a handler so that the reception can be broadcasted to multiple protocol handlers, and I also need to control some parameters of the CAN port. So this is what the control method is designed to do. But I'm just thinking if I could simplify this, but without having to change too much code in other places. So I want to see where this is used. So let's check. This would be. That will be basically just used in the STM32 implementation for now. No. Let's see. Okay. Let's see. Just used for getting status. This implementation is a bit messy. And instead of retrieving the container from CANOps, I now retrieve it from DevOps. This CAN device is pointing to DevOps. I'm still not very happy about my implementation of handler, because I'm using it both for no, I'm not very happy about it. Let's see, can send. CAN device handler is currently not implemented. So one of the issues with CAN and broadcasting the messages to protocol drivers is that it's a very bad idea to do it directly from any kind of CAN interrupt or something like that. And because it has to allow multiple protocol drivers to be registered with the CAN driver, it has to be implemented in such a way that anything that arrives gets pushed into a local queue inside the CAN driver, and then there is a dispatcher thread that takes things out of that queue and sends it farther to the protocol drivers. And doing it that way allows kind of deferring this processing of messages until after the interrupt is done, which allows in turn to then call any function in the system from this handler code, and the handler code doesn't need to care about whether it's running inside an interrupt or not. So the way I've implemented it before was to have a dispatcher thread for each CAN device, which then sits on a queue waiting for messages, and this has to be a rather high priority thread, so that whenever a message arrives on the CAN interface, it will be pushed to the local queue on the interface, and then once the interrupt is done, if this thread is the highest priority thread and there is no other threads running that are of higher priority than this thread, then this thread will be woken, and then it can process the message outside of the interrupt and dispatch the message to the listeners. And this works really well. It doesn't have that much of a delay. It's perfectly manageable, and it avoids the problem of calling any external code from the interrupt routine. So I'm going to add something similar, but I'm going to be moving out this dispatcher from the base device into a separate object. And actually this will be called like subscribe. So we subscribe to the interface. Let's see, CAN listener. And also, it's important to consider the fact that listeners they're not necessarily the CAN implementation drivers. So if a listener was just like STM32 implementation, then I could have just passed the CAN device handle to this to the listener function. But what I want to do instead is to have this listener object embedded in any other structure that is not necessarily related to the CAN device, so that the pointer to this structure can be passed to that handler function, and then that structure can easily retrieve the containing object and get a pointer to the self object of that structure. So that's why I've implemented this as a struct listener instead of just passing, for example, a function pointer and maybe creating this listener internally. And it can also be good to send the device handle to the listener, so I don't have to get it from elsewhere. Unnecessary. So listener add, listener remove. And I'll just add the listener to the dispatcher object, which I will then add to this implementation, the STM32 implementation of the CAN interface. Let's see, ret, unlock the data, and return value. And then here I'll just define the struct CAN dispatcher. And the dispatcher will be implemented in the CAN subsystem. The main role of the dispatcher would be just to go over the list of listeners and pick out the listeners that should handle the messages. By default, it's going to be just all listeners, so everybody gets the same message. But later I could implement filters as well. So struct CAN dispatcher. This would be listeners, list of listeners. This will be deleted. And then the dispatcher will take care of the functionality that was previously handled by the CAN device handler. And this does not need a mutex anymore because it's just going to be a data structure. And all the locking will have to happen on the way I implement locking is that I implement it at the boundary of the abstract interface. So anything that that can like any function, the only functions that are going to be called between different threads are going to be functions that are part of the abstract interfaces, which makes it very easy to review the locking and to make sure that there is no to make sure that there is nothing that that doesn't have a lock, which should have the locking functions or critical sections. Like so, anything that's part of the library, like this, for example, CAN dispatcher. As long as the CAN dispatcher is only visible inside one task, it's never going to be called by any other task unless that task calls some method which is exported by the first task as part of the public interface. And I find it to be a clean approach to implementing threading, kind of getting everything clearly separated. And that's also one of the reasons why I don't use like global non-static variables. I never use global non-static variables. I do use global variables sometimes, but in a very limited fashion. I only use them as static variables, and whenever I see something like, for example, system core clock, which was a global variable, I try to remove that if I can. And when I write code from scratch, I never use non-static global variables because there's just a recipe for failure. Okay, so add listener. This is not add listener. This is going to be dispatch. Int dispatcher. Add listener is just going to add the listener to the list. And this didn't have to be a function returning an int, but I'll leave it at that for now. This, on the other hand, is going to return, let's see, it's going to have a return value, but or does it need to have a return value here? No, actually, this doesn't even make any sense. So if a handler returns an error, like we don't know what handler it was that returned an error. And really, handlers, like, when it's one-to-many relationship, we don't really need any return value. I'm going to make this more small. The handler will have to log that error somewhere. So and then when I've initialized or created this CAN driver object, I'll also initialize the dispatcher here. Let's see. Bad idea. Should never create the dispatcher thread before the object is initialized. So I'm going to create the dispatcher last when I've initialized everything. Ops doesn't need to be initialized anymore. And dispatcher. Save the interface. So at this point, things have to be, for the most part, initialized, except then for the CAN device interface. So the dispatcher will start once CAN interrupts are enabled, and once CAN interrupts are enabled, the interrupt code can actually call or can actually try to retrieve the pointer to this object. So this object has to be initialized with all the necessary internal parameters. So any CAN messages can be sent to the queue. Okay. Redundant declaration. Oh, of course. Expected declaration specifiers or right, okay. So that was because I had a semicolon there. Yeah, it's better to recompile because all of the previous errors just mess up for a GCC. Listener handler process message. And then the pointer to this handler process message takes the listener as first argument, and I think I will also send the CAN device as well. So I need to add CAN device. This would be the device on which the message has arrived, because otherwise I don't. Or I could actually store this device as a member variable, but I think for now I'll just pass it to the process message. And also the dispatcher will have to implement the processing loop for the messages, which will wait on the interrupt queue, on the receive queue, which is filled in the interrupt. So let's see here. It's going to be like this. So previously I had the dispatcher, I think, here. So then instead of, this would be a CAN dispatcher process message. I think this actually does belong in the dispatcher, because it just let's see. Because it's just waiting for new messages from the CAN interface. So this could actually be an external loop. In which case, dispatcher initialization can actually accept the CAN interface, CAN device. Why should I really have a reception method? Right. So instead of making this dispatcher loop call some method in the CAN public interface, I will implement it like this. I will have a pop next message. So next message will retrieve. Let's see. Yeah, this will actually work really well. So next message will retrieve the next message from the CAN device, and it can accept the CAN device handle as the first argument. And because this method is going to be implemented by the specific CAN device implementation, the method which will be pointed to by this pointer will only ever get the dev argument which belongs to that particular implementation. So it will then just call container off and get the containing pointer, which will point to the actual implementation of the device. Struct CAN message message, and then next message. And instead of calling receive on queue here, I will just do if, actually like this. Bug on just generates a panic. And all of the initialization will actually happen before the system is started. So when the device tree is parsed, everything will be initialized, and then after that, no initialization is ever done. Alright, so next message accepts the self dev pointer, so that's a handle to the CAN device, and then it gets this message here. I can move the timeout also to the actual implementation of the CAN device. So CAN dispatcher process message. And now that I have it implemented like this, I would actually need to have a lock there. I'll move the initialization of the dispatcher thread from here to here. For now, using just hard-coded stack size. And hard-coded priority as well. And instead of process message, then I can just move this to the dispatcher. And I will lock it here because next message can block. It will block on the receive queue of the CAN device driver. So locking anything before that has the potential of actually resulting in a deadlock. So thread mutex lock, self lock, and just locking this data. Let's see. This is just good practice, I think. Just never just only locking the data that is actually being shared here. So And in fact, this lock is right now strictly, like, it's not strictly necessary, because initialization currently only happens once. But I'm going to add it anyway, because I could use this dispatcher in a different way later. And just having, let's put an unlock there. So it's thread, unlock. So when we're done with the loop, we'll have the mutex probably locked. Well, actually, it's always going to be locked. So I unlock it, and then the loop continues. And in order for this loop to work, next message has to always sleep on the receive queue. Because if it doesn't sleep, then this results in a busy loop. That's not good. But it will always sleep, as long as it's implemented as some kind of queue that receives messages from either a different thread or an interrupt handler. Okay. So I got the listener. I'll delete that code. And then my STM32 implementation will have the CAN dispatcher, which I'll initialize here. So I have to pass the self DevOps, because that is the value of the handle that gets returned by the CAN subsystem. So DevOps. And then handle message. Let's see. Oh, this is actually, let's see here. This would be like receive message. And the next message will accept CAN device as the first parameter. And struct CAN message. And then here I can then retrieve the pointer to the STM32 implementation. By using container of dev struct STM32 CAN DevOps. That's it. That's how everything fits together. So the whole concept of using container of is very powerful. Like, it's insanely powerful to keep the type safety and yet decouple the code. And then this will block on the queue. So let's see. This can just return thread queue receive self rx queue So the timeout is important because if the system like goes to sleep, then this type of timeout can actually wake up the system. So the timeout means that this method will run around 10 times per second. Actually, this is just, yeah, this should really be the maximum timeout. Which is defined. Let's see. Yeah, thread wait forever. This is the pointer that gets passed to the thread from here. So I'm passing it here, self, and then it ends up as PTR up there. Okay, hello Damien. I have a simple question. Do you really have to use a split supply for your circuit? Can't you use a different op-amp that doesn't require split supply? Or is that a requirement that you have? I guess that, yeah, I guess if you're using speakers, you do need a split supply. I personally don't like LM358. I chose, for this circuit, I chose this op-amp. So the TLV2474. It's a rail-to-rail op-amp, and I'm very happy with it. I think it's very nice. And since you mentioned LM358, I assume that you're kind of looking for some kind of generic op-amp. I don't know if any particular property of LM358 is attractive to you. And if it isn't, then maybe you could consider some op-amp like this, which is much better than LM358. CAN dispatcher has no member name. Next message. Oh, CM, of course. So the definition of the CAN device is now using reg that is going to be either CAN1, CAN2, or any other CAN device on the chip. So maybe uninitialized. Good point. Except, yes, good point. If I hadn't enabled the warnings on GCC, I would have missed that, which would have resulted in a crash, probably, or just the device not working. So lock. Let's see. I should get this from thread. Okay. Yeah, great. So I'll go back to where this was defined here. Let's write VFX. Oh, damn. So I must have pressed some shortcut here, which essentially just removed a portion of this file, and I did not realize that I did that. Let's see. Yeah, what makes sense here is actually just doing it this way. Okay, so at least it compiles. I'm gonna add the CAN interface to my device tree here. That would be a good place to add it. I can add it last. So I'll have CAN 1 and CAN 2. I'll start with CAN 1. Reg would be CAN 1. And also, CAN C. I'll add a little message here. Now, when it comes to configuring the CAN interface on STM32, you have to configure like the number of time quanta for sampling the signal. And to do that, I'm going to bring up the data sheet. Let's see. Okay. I just want to check for a device tree that I've written before, which uses my CAN driver, because I had a comment there in one of my device trees where I wrote how the calculation is done, because I never remember exactly how it's done. It depends on the main clock. Let's see. Okay. So this is how it will be done. So first of all, we'll have the prescaler, which will have some value, and then we have this time quantas for each one of these different. Let's see here, BS1. So the prescaler will divide p clock 1 to get the CAN clock, on which all of the time quanta will be based. Right, and that will be synchronization segment, I guess. What a synchronization jump width defines the upper bound to the amount of lengthening or shortening of the bit segments. Okay. I'm not going to go into too many details about this. If anybody who is interested can look up the CAN specification to get a better description of like prop seg, phase seg 1, phase seg 2, etc. The values that I've used before are for the SGV, SJW, I used 1, and segment I used 6. And right, so the sum of these values has to equal, let's see, it has to be like, let me think about this. So prescaler will divide the clock, p clock 1, and I want to have a baud rate of 1 megabit per second. So if I, right, okay, so yeah, here's how it works. So if we choose a prescaler, let's say like 3, and we have a clock that runs on, let's see here, print out the clock here. I think I'm running on like 49 megahertz, p clock 1. And so the prescaler, the clock will be divided by the prescaler, which means that CAN clock equals 49 megahertz divided by 3. And we could choose a prescaler that gives us some reasonable value. So let's see. We could maybe, I mean, I should be running perhaps at I should be running at 50 megahertz, but I had a little bit of trouble there. Maybe I'm getting some wrong values about the actual value of the clock. I need to double check that. But if I configure CAN based on the settings, then I can at least see if the clock is actually 49 megahertz. So 49 maybe divided by, what could I use? 49, is 49 prime? No, 49 is not prime. Because we can use yeah. So we can use a prescaler of 7, I guess, because that's something that gives us exact number. So I get 7 megahertz then, and then the sum of these values, so 1 plus 6 plus 7, or SJW BS1 BS2, has to now equal 7 in order to get 1 megabit per second. So if this clock is 7 megahertz, then if we divide that further by 7, we get 1 megabit per second baud rate. And we could use 3, 3. So this would work. This would give 1 megabit per second baud rate for this CAN interface. Compatible with STM32 CAN. So I don't really understand the question. You want to split the voltage rail, and then you still want to keep the you still want to have. So essentially, you want to have some kind of buck converter that converts that voltage rail into differential supply, positive and negative, and then you still want to use the power supply for something else. So what's the issue there? Did I understand that correctly? Can you not just use the power supply to power two different, like one for the one that goes to this differential supply that then feeds the op amp, and then use the same power supply to power something else? CAN ready. Okay, and then because I have two CAN interfaces, I want to add another one to the device tree. So that I have two of them. So I'll have CAN 1 and CAN 2. Now the issue here right now is that the GPIO pins are still not configured. So they need to be configured. And the GPIO pins that belong to CAN interfaces are visible here. Let's see, where's CAN 1? CAN 1, CAN 2. Here's CAN 2, PB1213. So I can just place CAN GPIO. This would be GPIO AF CAN 2. And should they be push-pull? I'll set them to GPIO type B, and pin control 1213. CAN 1 connected to CAN RX1. PD0 and PD1. This obviously needs to go to CAN 1. Two here, so. Okay. see. Where is YouTube? Okay, so you have L4960 output single-ended voltage. I want to use differential supply for the op-amps, but still be able to use that single-ended voltage. No, that's not virtual ground. Virtual ground is, let's see. Virtual ground would be in the middle, like between the negative and positive supply, but since you're probably converting, do you convert that voltage to something lower? Then that voltage wouldn't be the virtual ground. And virtual ground is only going to be at virtual ground if we have an ideal op-amp, I think, something like that. But I don't really. I'm not an expert in op-amps, so I can't really answer that question with a lot of certainty, I guess. But I guess it would depend what you would use that voltage for. So, like, technically, you could even connect, like, if you have a 5-volt regulator and you have a 12-volt supply, you could connect that 5-volt to the ground pin of an op-amp, and then the ground, the actual ground of the circuit will now be at -5 volts. So you kind of get, like, it's just difference in potential. So you could connect if you make this 5-volt voltage now the ground of the op-amp, then the actual ground of the rest of the circuit will be at -5 volts. So then you could feed the op-amp with a voltage that's lower than the voltage that is on the ground terminal of the op-amp. So maybe you can figure out what you need to do based on that. So before I can test the CAN interface, maybe I could test it. Maybe I could send a message on the CAN interface and just test it. If I don't have any other devices connected to the CAN bus, the CAN interface will just try to repeatedly send the same message, so I can at least see if it's working. CAN 1 and CAN 2. And then here I could add a small command. We'll just send a message on the CAN bus. I'll have to clean all of this up. This is just for testing. Timeout. The timeout for CAN only applies to waiting until there is a mailbox, or waiting until any outgoing messages have been sent and there is space to send more messages. So it doesn't actually guarantee that a message will arrive at the destination. So you want to use the 12 volt output to feed something else then? Is that what you're looking for? CAN 1 is missing. Of course it's missing because I didn't add it. So I added just labels, so I can reference the devices here. So this now points to the label of CAN 1 device, CAN 2 device. Okay, CAN 1 and 2 ready, FD CAN. I'm gonna just bring out my scope here. Most probably there is not going to be any result coming out of the canvas, but maybe, just maybe, it works from the first try. Let's see, here's a probe, and I'm gonna just open up my scope program. So what do you think? What do you think could be the problem for you with your current design? Like, what are you afraid of? Let's see. Where is my wriggle? Why? press remote. Alright. So I got the scope here. And I'm gonna put it the can H or can L. So nothing is coming out there, but it could be that I have to check. Let's see here. I got something here. So this would be CAN 1 and this would be CAN 2. So there is something being sent on CAN 1 but not on CAN 2, unfortunately. So this one is not working. And then if I go out on the there we go. So this is the actual output on the CAN bus. And this is before the transceiver. So at least something's coming out there. Obviously, I would need to connect the CAN bus to at least one other device in order to be able to test the transmission. But CAN 1 is working, CAN 2 is not working. And it could be, I mean, obviously it's not working because I didn't add the interrupt handlers for CAN 2. So I'm actually expecting the same interrupt handlers to, like the ones that I have defined for CAN 1, to work for CAN 2, which is not going to happen. So the CAN interfaces are working. I just need to add more code and bindings to the interrupt handlers, and then I should have CAN 2 as well. So that's it for this video. Well, the ground reference point is whatever you make the ground reference point. So like you can have let's say you have two regulators, and one outputs, as I said before, one outputs 5 volt, another outputs 12 volt. You can use the output of the 5 volt regulator as ground for a circuit. And you can use the output of the 12 volt regulator as the positive supply, and you will have 7 volt feeding that circuit. So your ground is essentially whatever you make your ground. Like, as long as the important thing is that the grounds are at the same potential between different circuits. So like if you have something connected with a cable, if one of the devices has ground that is at a different potential, then you will have problems in the communication. But ultimately, the potential of the ground is whatever you make it. Thanks, Adrian. My channel is not growing as fast as I would like it to. But the fun part is actually getting things working here. So I'm glad that these boards work as well as they do. There are a few issues, but nothing that affects the functionality. Nothing that cannot be fixed. Yeah, so obviously, let's see. So if you are splitting the rail, I guess you will have the potential of the op-amp ground at 6 volts. So you have minus 6 volts going to the main ground, and plus 6 volts going to the 12 volts. So of course you would have to have different grounds for the op-amp and the rest of the circuit. Well, Adrian, I've only been doing this for like 2 months, at least at the current level. So I haven't been doing this for too long, and I haven't been marketing my channel. Like, I should be marketing it more, I think. I should be telling everybody who's interested that there is a channel where I stream live, and you can learn a lot of things about hardware and software. Well, I haven't seen your rail splitting circuit, so it's kind of it's difficult to tell. It's difficult for me to get an idea of what is going to be happening with your supplies when you power it on. But send the link, I guess. I can have a quick look, but I won't spend too much time on it. But I could have a very quick look and let you know in the next video. Well, join them later. How do you mean? Like, the reason that you want to have positive and negative supply is precisely because you want to have the ability to feed a signal that goes below the ground. So it doesn't really make sense to join them. I don't know how you mean. Okay, I'm gonna stop the stream now, but I think the chat will be open for a while. The chat will, I think YouTube keeps it open for at least 5 minutes or so.